right, welcome to Scale by the Bay. Good morning. It's very early in the morning. Thank you for making it here. My name is Savin, and today, along with my colleague Ville, we are going to talk about the ML infrastructure that we've built at Netflix to handle a wide diversity of problems that our data scientists face. Now, all of you might be wondering, what are the actual data science problems that Netflix solves? For a lot of you, the first contact that you have with Netflix and ML at Netflix would be around recommendations that you see on our service. But that's mostly just tip of the iceberg. We are one of the world's biggest studio in the world. We have a content budget that is in the billions, so every single day our content executives need to make a decision how much to pay for any given piece of IP, how to efficiently produce any piece of content wherein a lot of data science goes in. We are also one of the biggest subscription services on the internet, so a lot of decisioning goes behind fighting fraud, account takeovers. We operate one of the biggest CDN services on the internet as well, so how do we optimally place our videos on those CDN caches? So our data scientists are inherently working on a really, really wide diversity of problems, and they inherently need an infrastructure that sort of like scales out and handles that diversity pretty easily. So my team, over the last 2 years, we have built this machine learning platform called Metaflow, which is predominantly targeted towards users in the Pythonic and the R world. And today, in this talk, we are going to focus on two major pillars of this platform, inherently reproducibility and scalability. So for the first 15 minutes, I'll focus on reproducibility, and then my colleague will talk about how we deal with some of the scalability concerns and our philosophy behind it. And all this while, we wanted to make sure that our data scientists can focus specifically on data science, and all the infrastructural concerns are sort of like transparent to them. So a big focus of this talk, as well as our platform, is on making sure that the constructs, the abstractions that are provided to our users are inherently highly usable by them. So let's begin. So a lot of you, like the software engineers as well as the data scientists in the room, would be familiar with, situations like these where you have some amount of code. Let's say you were training a model on TensorFlow, and all of a sudden next day it stopped working, even though you didn't really take any explicit action which sort of like mutated the state of your code. And what's happening behind the scenes is that your code inherently is interacting with external systems. In this case, TensorFlow brings in a myriad of dependencies. Many of them are unpinned, and they can change in often unforeseen ways, right? As software engineers, we are all tuned to identify those issues and fix those, because that's sort of like our bread and butter. But then when it comes to data scientists, then they are asked to be sort of like first-rate software engineers when they have to figure out like what has gone wrong and where. And that's sort of like asking for a lot from data scientists, and that has a clear impact on their productivity. If, let's say, a data scientist is following good hygiene, they are penning all of their dependencies, they're like very well versed in how to maintain and manage their systems, other people will have a really hard time replicating their environment and sort of like reproducing their results and then building on top of that. And that has sort of like given rise to this culture of team of one in many data science organizations, where every single data scientist is sort of like tasked with one singular project, and there's not a lot of collaboration happening on the model inherently per se. So these problems are inherently just rooted in this notion of reproducibility, where you want to make sure that you are able to execute what executed before in precisely the same way and expect more or less coherent results. And if we sort of like go deeper into like what this notion of reproducibility means at the end of the day, it's composed of two major portions: idempotency, which is inherently, if you are able to execute your code, then you are sort of like guaranteed consistent effects; and repeatability, which is merely the ability to actually execute something over and over again. And if we look at it a little bit more concretely, the notion of idempotency lies in the user code, which is then surrounded by a repeatable compute environment. And then this entire unit of work is something that you can take and execute on any sort of like physical execution system and sort of like be guaranteed consistent results over and over again. In the case of machine learning workflows, your machine learning workflow would inherently be a composition of these unit of works. And in this case, you might have a bunch of different steps like data prep, training model, fitting them, and then deploying them into some sort of like production system. And you want to sort of like guarantee that each of these nodes of your workflow are sort of like reproducible in certain sense so that then you don't really run into unintended behaviors. Now, if we look into what actually goes on in this unit of work and how do we actually go about thinking about making it reproducible, let's peel off the covers a little bit more. Let's look at like what exactly is in this repeatable environment. What are the dependencies of this idempotent user code that sort of like needs to be packaged and shipped around in a consistent manner? So notionally, the two big dependencies that any sort of code has in machine learning are like data dependencies and libraries. And it's not just the data dependencies, these are like fixed in time, they're also moving as time progresses. So for any sort of like notion of reproducibility, we need to figure out how to encapsulate and capture any changes in user code, libraries, as well as data dependencies, and how do we sort of like go about reasoning about those. Which sort of like leads us to inherently a versioning problem in the case of machine learning systems. So how do we deal with versioning for user code, for libraries, for data? And in the software engineering world, we have solutions for all of these three. So people are familiar with like version control. It's been around for like more than 3 decades. And Git is sort of like tour de force. For libraries, a lot of people use Docker to sort of like bake their dependencies and then execute their user code on top of that. And for data, when it comes to sort of like this functional paradigm of data engineering, people rely on immutable snapshots of data so that they can just like keep the pointer to data around and then just assume that data is sort of like frozen in time. All of these strategies, in isolation, they work well. But then a machine learning system is sort of like an amalgamation of the user code, libraries, and data. And we need sort of like a solution that sort of takes care of all of these three things in a similar manner without actually placing a lot of tax on the user, which in this case is going to be a data scientist. Let's actually walk through like what might be some of the big issues with some of these systems and see if we can sort of like come up with an alternative which might sort of like give us the exact same capabilities that these systems provide, but with a much better usability function. Now, let's say I'm a data scientist. My work is exploratory in nature. I'll be writing some code, and then I'll be executing it with a bunch of hyperparameters. At the end of it, I'll have a model. I'll evaluate it using some metrics. If I'm dissatisfied, then I'll tweak some hyperparameters. I'll tweak some code. So during any given day, I am making a lot of changes to my code, and I want to step back and see what my state of code was in any of my previous experiments. And one obvious way to do that is every single time I execute my code right before that, I'm sort of like doing a git commit and storing that commit somewhere, annotating it with like what were the hyperparameters, what was the context of that execution. But now the big problem here is that if I forget to do a git commit at any point in time, I've sort of like lost state. And we can definitely rely on like some homegrown discipline in data scientists to sort of like get around this issue. But even then, it's not really that usable, right? Like, as a data scientist, I shouldn't be just looking at like, okay, what's a git push, what's a git commit, what's a git pull. That's just like asking for a lot. So one thing that we can do here, which is like very similar to how people think about data, is just treating data and just treating code and any sort of like hyperparameters as data in itself. And what we do in our machine learning platform is every single time there's any execution of code, we inherently snapshot that entire code and we ship it around as we ship around data and treat it in exactly the same way. Let's talk about Docker, about how do we manage libraries, right? So this is like one standard way where a data scientist will come in. Let's say they are training a model using pandas in TensorFlow. They'll create a Docker file, pip install pandas, pip install TensorFlow. They'll have some CI/CD process. They'll create an image, and then they'll execute their machine learning model on top of that image, maybe a training process or some evaluation process. All of this is doable. It's not really asking for more, but still it has a lot of overhead, a lot of unforeseen overhead. The number one is that, okay, do you create one Docker image for your entire machine learning pipeline? As you saw before, a machine learning pipeline has a variety of different states. You might be training a model, you might be deploying a model. All of these different states, they bring in different dependencies. So now do you create one Docker file with all of those different dependencies? If you do, then you run into dependency management hell, where you're constantly trying to figure out how those transitive dependencies are sort of like dealing with one another. If you choose to go with an alternative approach where every single node has its own sort of like Docker image, then you run into an image management hell, because now you have to constantly figure out like, okay, which step has what image? Is that image being maintained? If you have any updates, are those being propagated to all of the images or not? So one way or the other, you have to sort of like pick your poison, whether you want to be dealing with like many dependencies in one image or multiple images. Irrespective of that, there are certain other issues that you will soon run into as a data scientist. Let's say you had pandas and TensorFlow, and you decided that, hey, I want a newer version of pandas. Maybe there's some new functionality that you want to use. Now, as soon as you switch to a newer version of pandas, and you decide to build your Docker image again, you would end up bringing in an entirely new version of TensorFlow just because you hadn't pinned your version of TensorFlow, right? So you can definitely rely on pinning your dependencies, but that sort of like doesn't really get you all the way, because all of these packages that you're bringing in, they have transitive dependencies, and often these transitive dependencies are not really pinned. So every single time you build your Docker file, you are sort of like not really guaranteed the same result. So while we are talking about idempotency in user code, like we need to make sure that our infrastructure, our library declarations are sort of like also idempotent in some nature. Also, when it comes to machine learning code, you're not inherently, even though you might be writing your code in Python, your dependencies are not always in the Pythonic world. If you want to use TensorFlow GPU, then you need to understand what version of CUDA DNN you're trying to bring in. And at times, this means that you're not only in the pip ecosystem of like trying to figure out what your dependencies are, but you need to now sort of like learn and intimately understand what are some of the other package managers apt-get in this example. Again, most of these problems that I'm referring to are problems that a lot of people deal with. These problems have existed for a really long time, and people have built solutions as well for these. For example, Conda is a package manager that works across Python as well as system package dependencies. And it works really well and is being embraced by a lot of data scientists. But now when you look at it, look at the score of the problem, let's say you're using Conda, then what is exactly Docker bringing into the equation? Then Docker is inherently kind of like an overhead that is causing death by 1,000 cuts to our data scientists. And that's sort of like the approach that we took when we were building Metaflow, where we inherently came up with this UX where we ask our users to inherently just specify their dependencies using a decorator, at Conda in this case, specifying what sort of libraries and Python version they want. And then behind the scenes, we actually snapshot all the dependencies. We create an equivalent of dependency log file, and then we ship this entire execution environment wherever they want to execute, whether it's on their local box or whether it's on some sort of container orchestration system. The input to their code, as discussed before, could be any sort of like immutable snapshots, which can reside in any sort of cloud environment. And their entire code, every single time they execute, we actually package this entire code, the libraries, and the pointer to the big data, and we just move it all around. And that sort of like leads me to the next question, like, okay, what is the physical substrate over which you actually end up executing your code? And for that, I have Ville who will talk about it.
Yeah, thanks, Savin. So, yeah, let me get the, that's fine. So, what Savin was talking about is a software solution for having these reproducible units of computation in a machine learning workflow. So that's all software, but of course, I mean, the software, ultimately, it needs to execute on some hardware, so it's not like an abstract thing. So ultimately, we need some kind of a server, like we do need to execute this code somewhere. And now if we take a little bit of a step back, what does it actually mean to execute arbitrary user code on the server? Of course, there's a question that, well, do we know that the server is big enough? Do we know that it scales? And hence, this part is about scalability. So now, if you consider that like you have these units of computation that Savin was talking about there in the middle, and in order to be able to execute this whole thing with the user-defined code as well as the dependencies on some server, you need a big enough server. So you have this circle and like you find a big enough server to execute the code on. And now like the question of scalability is that what happens when the circle grows? What if you need more memory? What if you need more CPU? What if you need more GPUs? And now, as my 6-year-old could tell me, if you have a big circle and like you need the box around it, you need a bigger box. So you need a big server to run these like big units of computation. And this approach to scalability has been, of course, around since the very beginning of computing, and it's called the vertical scalability, which means that like we just keep finding bigger and bigger servers every time we have a bigger unit of computation. Now, many of you, of course, like can imagine that the problem is that you can't just like keep finding bigger and bigger servers infinitely, so it might be problematic. So now what people, especially in this conference series, have been talking and thinking about for like at least the past 10 years is this idea of horizontal scalability, where instead of like trying to find always bigger and bigger boxes, what if you can divide and conquer? What if you can shard your problem in much smaller pieces, and then you can find like uniform sized boxes to execute this computation on. And this model is particularly appealing if you have a data center that just happens to have, let's say, 10,000 servers, and you know that it's very homogeneous and makes operations easier. So each one of these servers have 32 gigabytes of RAM. So now you just like split any problem to small enough chunks that you can execute them, let's say, using less than 32 gigabytes of RAM, and off you go. So technically sounds good. Well, now the question is that like what could be problems with this horizontal scalability approach? So for instance, like a couple of years back, there was this like interesting paper, you can Google it, Scalability, but at what cost? And what this paper was showing that for certain kind of a graph processing, graph querying problems, a single threaded implementation performed better than these horizontally scalable systems. So how could that be? I mean, how can you beat with a single CPU a cluster of many CPUs? And the reason for that is simply that the horizontal scalability comes with overhead. So every time you have network communication, you have network overhead. Like now when you have to kind of shard your problem in different ways, I mean, that comes with an overhead. And now it might be that the overhead ends up dominating the kind of the total cost of computation unless you do it very, very carefully. And that's only about performance. So now there are other kinds of overhead as well. So this paper is all about performance, but also, as you know, there's operational overhead in managing these distributed clusters. So any of you have maintained a Spark cluster or Presto cluster know that, well, I mean, things can go wrong, and like you need to have expertise to know how to debug these things. And of course, if there's a certain probability that the single server goes down, and let's say it goes down once a month, and you have a single server, then you can expect that it goes down once a month. If you have 100 of those servers, you can be pretty much sure that like something goes wrong every day. And of course, like over the past 20 years or so, we have learned how to deal with these issues on a software layer. But I would argue that one thing that's missing, I mean, although we technically know how to do it, is that like we haven't quite solved the usability question. How do we make these distributed horizontally scalable systems usable as things that are vertically scalable? So just to give you an example, that if you had a small enough data set, let's say it's 100 megabytes, 4 gigabytes, so really small. Now the question is that would you use a horizontally scalable system to analyze this data set? And now what you might be thinking is that like, well, if you have a Spark cluster already and there's no downside using it, that's fair. But I mean, let's just say that like you're a data scientist, this is what you need to do. I mean, like probably the easiest way what you might consider is that you have your laptop, and your laptop has 16 gigabytes of RAM. And now you get the 4 gigabyte data set, so it's a no-brainer. You open a Jupyter notebook, you load your 4 gigabyte data set in a pandas data frame, and like you have a lot of like headroom there, like to do even copies of the data frame, and you can do everything in your notebook. You don't even have to think about anything. It just works beautifully. And like if something goes wrong, you can understand the Python stack traces. Probably the biggest issue when it comes to the hardware is that your laptop runs out of battery, and you can understand like what's going on. Now the question about scalability. Well, the thing is that like if, let's say instead of 4 gigabytes, it's 10 gigabytes. Now even with the 10 gigabyte data frame, you do exactly the same thing. You execute the same Jupyter notebook, the same code, nothing changes, the failure patterns are the same. It's all like works beautifully. Maybe it's slightly slower because now you have twice the amount of data. Well, obviously, like you can see where this is going. So eventually you have like a big enough data frame that like it doesn't fit in memory anymore, and like then your like a notebook fails in a mysterious way, you get out of memory error and so forth. And now if any of you have worked as a kind of an infrastructure DevOps person in an environment like and helping data scientists, then typically the next discussion that happens is something of this kind. So you have the data scientist in the blue shirt coming to you saying that, okay, the data set is too large for my laptop, and could I get the bigger laptop so I can just execute my Jupyter notebook because it worked for 4 gigabytes, it worked for 10 gigabytes. Well, I mean, I could just like kind of get it running for 20 gigabytes as well. Well, now you, as a responsible DevOps person, your answer is that, look, you are doing it wrong. I mean, like that line of thinking is not scalable. So even if I had in my back room like a laptop with 32 gigabytes of RAM and I gave it to you, yes, you could execute it with 20 gigabyte dataset, but next time when you have a 6 gigabyte dataset, the same thing would happen all over again. And like I can't keep giving you bigger and bigger laptops all the time. So change your approach. You should like use Spark, do something differently. And now it's fair, and technically speaking, even the data scientist knows that, yeah, that line of reasoning kind of makes sense, but the fact is that I just wanted to go home and watch Netflix, so can I just please execute my Jupyter notebook, and can I just get the bigger laptop? And in the usability point of view, that is exactly right. I mean, that's what we would like to have. And now the problem with this is obviously that, well, actually the laptop that I had about 10 years ago is actually not that different than the laptop that I have today. I mean, they just like haven't like changed so much. But there are actually other things that have changed quite drastically over the past 10 years. So instead of like running this stuff on a laptop, what we do at Netflix, as you may know, Netflix is pretty much 100% on Amazon Web Services. So the question is that like, well, I mean, what does this mean in the context of a cloud? And here's an interesting chart that I pulled like for you for this presentation. And what it shows is that it shows Amazon Web Services since the beginning of time, since 2006 when Amazon Web Services launched in public beta. And it goes all the way on the x-axis to 2019, which is today. And on the y-axis, we have the maximum amount of memory that's available on the largest kind of a normal general purpose instance on Amazon EC2 at any given point in time. And now the small disclaimer here is that by general purpose instance, I mean that Amazon has these special instances like FPGA instances, bare metal instances, so forth. For many practical purposes, it might not be like very convenient to use them for like this general compute. So let's just focus on the basic instances like M instances and R instances and so forth. And now in 2006, Amazon launched with one instance type. It was the M1 small that had 1.7 gigabytes of RAM. And then like about a year later, they launched the M1 8X large with 15 gigabytes of RAM. Then like 2010, M2 4X large, 68 gigabytes of RAM. Then finally 2013, like I remember being super excited when they launched CR1 8X large with 244 gigabytes of RAM. And I believe I was probably like one of the biggest users like of these instances at my previous job for the longest time, because it was only in 2016 and 17 when they finally launched the R4 16 extra large with 488 gigabytes of RAM. And now this year they launched the R5 24X large with 768 gigabytes of RAM. And now a couple of things here. Well, I mean, the first thing is that like you can see that this is pretty much following an exponential curve. And the other, just a thought exercise for you, is that like many of you have been coming to this conference, like remember for instance that the original Google MapReduce paper came out 2004, Hadoop started gaining traction in 2007, 2008. So now if you imagine yourself standing there in like 2007, 2008 timeframe, you might think that the horizontal scalability is the only way to go, because all we have available easily in our own data center and in AWS are these small instances with 1.7 gigabytes of RAM. So really it felt that that's the only way to go. But now, something that's really important to consider is that now today we have 500 times more memory on these machines than like what it used to be about 12 years ago. So big difference there. So what does this mean in practice? So now imagine this like a very practical use case scenario for Netflix. So we have like many machine learning problems that are of the nature that we want to analyze what our users, what our members are doing, what kind of content they would like to see. So imagine that you have this data frame that has every single Netflix member as a row, and today we have about 150 million members. and then some number of features for every member as a column. So a big data frame, and like for convenience of the math, imagine that you have 1 byte per column. So now if you imagine that like we have 1,000 features for every user, and like we have kept like every single subscriber in memory. The interesting thing here is that ever since the very beginning of AWS, we have been able to keep this data frame in memory. So since 2008 all the way now to 2019, we have been able to keep this data frame with all Netflix subscribers and maybe 1,000 features in memory. So that's pretty interesting. And now, of course, you might think that, well, I mean, yeah, but it's only because like 1 kilobyte is not a lot of data. So what happens if we had 3 kilobytes of data per member? Well, now, interesting thing here is that like you can see that around like 2008, 2009, we had a situation like where we couldn't keep the data frame in memory. And like you might think that if you are a distributed systems engineer, like standing there 2008, 2009, like you can't keep the data in memory, the feeling might be that, well, we just have to change our strategy. We have to change our paradigm because we have reached the point, kind of the escape velocity, that the amount of data is so large that we possibly can't keep working this way anymore. And somehow the idea is that the data just keeps growing, but the machines don't keep growing. So it's really that it's like a shooting up in the sky, but the machines stay small. And there's like a kind of a slight bias in thinking there, because actually the machines are growing exponentially as well. In this case, looking at the memory dimension. And like although companies like Netflix are growing pretty exponentially too, I mean, they kind of keep at the same pace. Now, of course, you can imagine that you can keep going here. Let's say we have 4 kilobytes of data per user, like, well, definitely getting harder. You can imagine at 10 kilobytes, it's like 100 kilobytes, this chart is getting all red and it doesn't work. So it's easy to have the counter argument that, of course, like a vertical scalability isn't a silver bullet and you can't solve everything with that approach. And that's, of course, absolutely true. But the point that I'm trying to make here is that the number of different and the volume of different workloads that you are able to handle with this very usable vertical scalability approach is actually growing exponentially. And of course at Netflix we can't solve every single problem with this approach, but what's really important is that we can solve an increasing number of problems with this approach. So like here the yellow chart, it like depicts all those cases where we can like provide a really nice experience for the data scientist by saying that, look, it works exactly the same way as on your laptop. So there's no new paradigm, you don't have to change anything. Very convenient. So what does this mean in practice in Metaflow? So in the same way as Savin was explaining that you can define your execution environment, you can just define that, okay, I need 10 gigabytes of RAM to execute this function. And like we give you the right size server. Or like maybe if you need 500 gigabytes RAM, we can give you a server with 500 gigabytes. And of course all this works in the container management system. So like we just provision them on the fly from the cloud and so forth. So very, very straightforward. And now an important like additional dimension here is that because this is the cloud, they are not physical laptops, not only we can give you one laptop, quote unquote laptop, but we can give you any number of these machines in parallel. And now there is a subtle and important difference to the idea of horizontal scalability. So whereas like with the horizontal scalability, the idea is that you are kind of sharding your problem automatically, let's say with what Spark does with RRDs and like other ways of like splitting the problem automatically. Here we are treating these user-defined functions as atomic units of computation, like Savin was saying. So we are not like trying to automatically split them, but we are just like having multiple copies of the same computation, maybe with different parameterizations. And this is very convenient in many machine learning workflows where, let's say, you want to do things like hyperparameter search. So that allows our users both like write their code in a very straightforward way, the same way how they would be writing it on their notebook. And like when they need more resources, they can just say that, okay, give me a quote unquote a bigger laptop. And like let's say they want to like train the same model for every country in the world, or they want to like run it in any way they want to do the fan out. I mean that's easily doable, and we provide abstraction for that in the Python code base. And now this kind of concludes my talk. So Savin like started by talking about the reproducibility, which is that how do we make it very easy for users to define these closures that both include their user code as well as the full environment, the repeatable execution environment that makes sure that the results are always reproducible and you can make sure that you are not interfering with production. And then I talked about the scalability side of things. How do we make sure that like we always have the hardware at our disposal so we can actually execute these units of computation. And like the overarching theme theme here is not to say that we are proposing something that's very new or different than technically what people have done before, but really the kind of the backdrop here is the human centricity. The idea is that like, how do we make it as usable as possible? That's it. Thank you.
Thank you, Ville and Savin. We have time for one question. Is there any question in the floor? None? All right, thank you very much.
Thanks.